Pretty cool green screen, right?
Searching for things is hard. And by hard, I mean slow. Say you were given a dictionary and you were tasked to find every single three-syllable word. It's not a difficult task, but it would be arduous. By instinct, I'm willing to bet that you'd go through every single word in succession, picking out the words that best fit the bill. This is exactly how early search engines worked in the 90s. The search engine would take a look at the phrase that you gave it, and then compared it against every single website that it has, and then it would return the websites that had the most amount of instances of the words and phrases that you gave to the search engine. That methodology of searching is called text-based ranking. There is a problem with this, however, because say you searched Wikipedia, and this is how search engines use to search the internet, you might be surprised to find that most of the results on the front page are hate blogs written by elementary school teachers claiming that Wikipedia is a terrible source for elementary school projects. The only reason you'd find these first before Wikipedia is because such fictional hate blogs use the word Wikipedia more than Wikipedia does. This is a problem. You don't want to read hate blogs, you want to read Wikipedia. That would be a really silly way of implementing a search engine, and software engineers know that. That's why modern search engines use a way of ranking websites based on relevancy to the search that you gave. That relevance may be determined via metrics like authority, how often it's quoted from other websites. It can be anything. Using those metrics, however, it can make a ranking of which websites best fit whatever you're searching for. One such algorithm that uses that methodology is called the PageRank algorithm. The PageRank algorithm was developed by Larry Page and Sergey Brin. Larry and Sergey were friends while they were graduate students at Stanford. These two would go on to be the founders of Google, using the algorithm they developed to base their search engine off of. Side fun fact, Google is named after the number Google, which is a number with 1 at the beginning and 100 zeros following it. The number Google is named after a fictional character named Barney Google, which is what happens when you let 9-year-olds name numbers. But that's a story for a different day. The PageRank algorithm essentially treats the internet as a directed graph. A directed graph is a way of displaying data and relationships between data. Each point of data is called a node, and how one piece of data relates to another is called an edge. In the particular context we're talking about, we can think about specific websites as nodes and links to other websites as edges. For example, say someone on Facebook posts a link to YouTube. We can think as Facebook and YouTube as two different independent nodes, and that link is an edge that goes from Facebook to YouTube. That's where the word directed comes from in directed graph. It has a specific direction from one node to another. The basic philosophy of PageRank is that if one node has a lot of edges pointing at it, if essentially one website is quoted a lot on other websites, then we can assume that that website has some sense of authority or importance, which is why if you search for Wikipedia, it's the first thing that pops up. It is considered to be a source of authoritative information. However, PageRank also incorporates another system wherein authoritative websites, if they link to another website, that authority is transferred along that edge. So if Wikipedia has a link to another website, since we're assuming Wikipedia is authoritative, we have to assume that the website that it links to is also authoritative. That authority transfers from Wikipedia to the other site. Let's use a more in-depth example to show what I mean. Say the internet in its entirety only has 4 pages. Pages 1, 2, 3, and 4. You can see that these pages link to one another in a unique way. We can display these relationships as a directed graph, and here is what that would look like. We're also going to make the assumption that one node evenly divides its authority among all the nodes that it sends to. So page 1 points to 2, 3, and 4. We can assume that page 1 divides up its authority in thirds, and that goes on for how many websites it points to. If you have 1 million different links that page 1 has, then the total authority would be divided up a million ways. So let's go ahead and take a look at what those authority transfers look like on the graph. Looks like that. And we'll treat those numbers that you see by the edges as weights for the edges. We can actually represent those weights in what's called a transition matrix. Each successive column in a transition matrix represents a source node, and each successive row represents a destination. So if there is a number in column 3 that correlates to row 2, then you know that node 3 points to node 2 in some way. So every 0 entry in this matrix represents an edge that doesn't exist. You'll see that since page 3 only points to page 1, there's only a weight of 1 that points from 3 to 1, on and so forth. Transition matrices aren't really meant to be that visually comprehensible, at least not as much as a directed graph would be, but they have some special properties that are very useful. Let's put those properties to good use then. Let's call our transition matrix A. To start out, we'll assume that each page has equal importance. So since there are 4 pages, each page has a quarter of the total authority of the internet, whatever that means. We can store this initial value for each page in a vector, and we'll call this vector v. If we multiply A against V, the resultant vector much more accurately reflects the importance of each page. And you'll notice that every single time we multiply A against V, it gets more and more accurate and starts approaching a singular equilibrium value. This is because multiplying A to V is the exact same as taking the current value, all the current values in that vector, and adding to them the importance of the incoming edges. That's why performing it over and over again iteratively eventually gives you a vector that is stable. It'll approach a value that won't change no matter how many more times you multiply it, and extremely accurate in telling you how important, how authoritative each page is. One important thing of note is that the matrix A has an eigenvalue of 1. This is because A is what's known as a Markov matrix. Markov matrices can have many different eigenvalues beyond just a singular 1 eigenvalue, but what's common among every single one is that they all have at least that one value equal to 1. This property is mostly derived from the fact that Markov matrices have columns that all add up to 1, and all the entries in the matrix are greater than 0 or equal to 0. We can look at this example from another point of view as well. We can think of this problem as a system of equations. In this system of equations, we assume the authority of page 1 to be equal to x1, and on and so forth. This system of equations that we just generated is essentially asking the exact same question as this equation right here. As I mentioned earlier, the matrix A has the eigenvalue of 1, and its respective eigenvector takes on this form right here. If we set this constant c to be 1 over 31, we find that we get back that original v value, that one vector that we derived earlier. That value of 131 is just derived from finding the exact constant that makes that vertex equal when summed up to 1. One thing that's really surprising about this PageRank vector that we calculated is that it claims that page 1 is the most important page, and that should be a little strange to you. This is because page 3 has 3 incoming edges. Page 1 only has 2. So why is that? If we look at the graph again, you'll note that 3 only has a single edge pointing towards 1. Going off of the assumption that authority is always transferred along edges, since 3 pours all of its authority into one space, that authority goes to page 1, making it more important than 3. This system works pretty well in the context that we just talked about, but there are some loose ends that we need to clean up. Literally. The first problem that we're going to deal with is dangling nodes. Dangling nodes are just nodes that don't have any outgoing edges. There are no links in them. If you use the iterative method of trying to calculate what the PageRank vector for this problem is, you'll find that every single page has an importance of 0, which is patently false. Page 3 has at least 2 nodes pointing at it, so it must have some importance. It can't be 0. So, how do we fix this? The simple solution is to just set column 3 of our transition matrix to be all equal values of 1/3. In a way, we can think of page 3 as pointing to every single other node, including itself. That not only divides page 3's authority evenly among every other node, it completely gets rid of the problem of zeroing out eventually. There's also another problem with disconnected components. Look at this graph right here. How would one organically go from node 1 to node 5? You can't. It's impossible. There's no edge leading from 1 to node 5, no matter what path you take. Linear algebra fails to solve this problem because if you take a look at the transition matrix, you'll notice that eigenvectors of the matrix are not scalar multiples of one another, despite the fact that both eigenvectors are derived from an eigenvalue of 1. This is a problem. This means that the answer is ambiguous. It has to be solved by the developer of the program. Larry and Sergey's solution to this problem involved inventing a variable that they called the damping factor. I'll explain more what the damping factor means or what it even is, but just understand it to be a constant set in between 0 and 1. Using that damping factor, or P, you can define a new matrix that'll get rid of the problem of disconnected nodes. Most often, this p-value is set to 0.15. So this new PageRank matrix, M, makes the assumption that the user will, most of the time, just go from one node to another, following along links. However, it also makes the assumption that there are times when a user teleports to other websites. These are instances when a user quits out of the current page that they're on and randomly goes to another page that exists in the internet. The damping factor that we talked about represents this probability. It eventually estimates that with a value of 0.015, there's a 15% chance that given whatever page you're on in the internet, you're just going to quit out and pick another one. Since a user could feasibly teleport to whatever website that they want, there is a 1/n chance that they go anywhere, n being the total number of websites that exist. And that is where the matrix B comes from. This is a very neat solution. For one thing, it completely gets rid of the problem with disconnected nodes because you can teleport anywhere. As well, it naturally gets rid of the problem with dangling nodes, which now have a p/n chance of teleporting anywhere else within the internet. Fortunately enough, there's also some really handy mathematical theorems that apply to this matrix M. The Perrin-Frobenius theorem states that if M is a positive column stochastic matrix, then it has an eigenvalue of 1. At least. As well, that value of 1 is the largest eigenvalue that it has. And the eigenvectors that correspond to that eigenvalue of 1 are either entirely positive or entirely negative. In particular, this means that there exists some eigenvector whose entries all add up to 1. These properties are vital to figuring out a PageRank vector. In just the last problem, you can see how useful it is to have that eigenvalue of 1 and its corresponding eigenvector. Otherwise, without these properties, it is essentially impossible to make a functioning logical ranking of all the websites that you have at your disposal. We have another mathematical theorem that'll help us called the power convergence theorem. This theorem states that if M is a positive column stochastic square matrix, you can set its probabilistic eigenvector corresponding to the eigenvalue of 1 to v, and set a column vector whose entries are all 1/n to be z. Then the sequence z, mz, m squared z, m to the third z, and then m to the kz finally, will converge to a singular value. This is the theorem that let us earlier repeatedly multiply our transition matrix to that vector to eventually get a singular equilibrium value that told us the basic ranking of all the websites. We can thus conclude then that the PageRank vector for a web graph with transition matrix A and damping factor P is the unique probabilistic eigenvector of the matrix M corresponding to the eigenvalue 1. Now, let's do an example to really solidify the concepts that I've gone over. We are going to calculate the page rank of this graph right here, assuming that the damping factor is equal to 0.15. We will start by making our transition matrix and call it A. Fortunately enough for us, it is quite simple. Each node in this graph only has one edge protruding from it, so we can set every single non-zero value in here to be equal to 1. This is very nice. We'll then make matrix B. As you can see, is filled with 1 over 8. This is because there are 8 nodes total. We'll then multiply our damping factor to A and B to get the following matrices right here, and then add these two matrices together to get M. You might notice a problem here. Column 1 is not column stochastic. It does not add up to 1. It does not even kind of add up to 1. The source that I studied even claimed that this was correct. It reads, a node with no outgoing edges has now p over n probability to move to any other node. The value of 3 over 160 is in fact exactly equal to p over n, 0.15 over 8. But p over n times 8 is not equal to 1. It is equal to 21 over 160. However, for any of our mathematical theorems to work, m needs to be column stochastic. That is just a baseline for any of this mumbo jumbo to work. Frankly, I have no idea how to rectify this. The source I read from said that this was correct and to be expected, but if you use this matrix and try to use those theorems, you'll find that no conversion ever occurs. The values will continually get smaller until it reaches 0. Well, not quite 0, but it gets quite small. The best that I can do is use the previously established easy way of just setting that whole column to be equal to 1 over 8. Node 1 now has an equal chance of going to any other node in the tree. We'll just have to be fine with this. We'll then use the power method convergence theorem and multiply m against v to get our PageRank vector. I'm just going to set the power to be 23, because why not? It's really high power, so it should be very accurate. When we do that, we get the following, which looks good. We find that node 1 has the highest level of authority in this vector, followed by 3 and then 2. This is a very sensible ranking, and I probably could have told you that without doing all these calculations. Every single node in this graph right here only has one outgoing edge. It transfers all of its authority onto the next. This is a repeating cycle in the entire graph until it reaches 1, which has no outgoing nodes. We can think of all that authority just pooling right there, even though that we technically declared that 1 has an equal chance of going anywhere else. It is diffused so much that 1 still pools it all up. The only reason 2 and 3 have a notable amount of authority is because of the number of vectors that point to them. 3 has 3 vectors that points to it, 2 has 2. And so they have a decent level of authority, but not as much as 1. 1 gets all of it. Kind of. So that is how the PageRank algorithm works. That is how you search the internet, or how your search engine searches the internet for you. I hope you thought it was interesting and learned something new. Thank you for watching. Do you like my green screen?